Why is it said that, even if the Earth is destroyed, humanity will never be able to fly out of the Milky Way? Because currently, the fastest object launched by humanity, Voyager 1, its top speed is only a few dozen kilometers per second. Sounds fast, right? But at this velocity, to fly to Proxima Centauri, our nearest star, it would take roughly 70,000 years to arrive. And that's just the Milky Way's next-door neighbor. Forget about places farther out. Some might wonder, what if we could build a spacecraft that approaches the speed of light? That sounds like a science fiction blockbuster premise. Yet, even if we could actually reach 300,000 kilometers per second to break free from the entire Milky Way, would still require over 100,000 years of travel. Crossing that dark void between galaxies is practically an unreachable distance. However, just as scientists were calculating these staggering figures, an observation in 2013 pushed the discussion to a far more outrageous level. That year, astronomers discovered that our Milky Way galaxy is surrounded by a colossal cosmic void. The sheer volume of this structure is unimaginable. It might be 2 billion light-years in diameter. If you tried to fill it, placing Milky Ways back to back, you'd need over 20,000 of them to span the distance from one end to the other. What's even more compelling, evidence suggests that we might be situated right in the center of this void. If this hypothesis is correct, then the cosmic expansion rate we typically measure, the distribution of galaxies, could all be versions seen from within a cosmic valley. No matter how precise the values are, they may not represent the true nature of the entire universe. But the truly captivating question lies ahead. Beyond the boundary of this void, could the density structure, or even the very laws of physics, be completely different from the universe we know? In the last few decades of cosmic research, there is one finding that still sends shivers through the astronomical community. It's called the KBC Void. This hypothesis was first proposed by 3 researchers, Ryan Keenan, Amy Barger, and Lennox Cowie. When they brought the existence of this region to the forefront, the entire academic community exploded. Because this isn't simply a case of fewer stars in a particular area. It directly challenges our fundamental understanding of the cosmic order. Theoretically, if the universe is uniform on sufficiently large scales, then no matter where a telescope is aimed, the galaxy distribution should appear roughly the same. This idea is what's known as the cosmological principle. Following the initial Big Bang, energy rippled outwards like a stone dropped in a pool, spreading uniformly in all directions. It was also believed that matter would fill space just as uniformly. It is precisely for this reason that scientists dared to apply the same set of physical laws to both nearby stars and objects at the edge of the universe. We initially thought this set of rules held everywhere. However, observations in recent years have gradually torn apart that notion. A growing body of data indicates that the matter in the universe is not as uniform as once believed. Some regions have dense galaxy clusters, while others are sparse. And among these non-uniform regions, the KBC Void stands out dramatically. It is not merely a space with less matter. It's more like a colossal, empty cavern beyond imagination. Observational data indicates this void is approximately spherical, with a radius possibly reaching 1 billion light-years. That's 4 times larger than the Laniakea supercluster, which contains 100,000 galaxies. It accounts for approximately 2% of the volume of the entire observable universe. What's more astonishing, we ourselves reside inside this void. Astrophysicist Andras Balog of the University of St. Andrews calculated that the stellar and galaxy density here is about 20% lower than the average density outside. That difference may not sound outrageous, but on such massive scales, this is an anomaly too significant to ignore. What's more intriguing, this void might be secretly linked to modern cosmology's greatest mystery, the Hubble Tension. The universe has been expanding since the Big Bang. This expansion rate is known as the Hubble constant. Scientists measure it using 2 entirely different methods. One involves observing relatively nearby objects, like supernovae and nearby galaxies, to measure the speed at which they recede from each other. The resulting value is approximately 45 kilometers per second per megaparsec. The other method analyzes the cosmic microwave background, the ancient light left over from the Big Bang. By extrapolating today's expansion rate from early universe models, the result obtained is only about 41 kilometers per second. The 2 sets of measurements differ by about 8%. This is the so-called Hubble tension. If we only consider the CMB prediction, the universe's expansion should be slower. Yet, the galaxies we directly observe are flying apart at a faster rate. Why does the same universe yield 2 different bills? A growing number of researchers suspect that the issue might stem from our local cosmic environment. Just as massive stars attract planets, the higher density regions outside the void would gravitationally pull on the galaxies inside. This adds extra acceleration on top of the universe's natural expansion. If this is the case, our measured Hubble constant would be subtly inflated, appearing faster than the early universe prediction. However, the situation is not that simple. Brian Keating, an astronomer at UC San Diego, believes that the void could indeed explain some of the discrepancy, but the extent of its influence is still undecided by the scientific community. Different models yield different void sizes and gravitational effects, and subtle shifts in model choice are enough to produce noticeably different conclusions. Recent observations even suggest that the scale of the KBC Void might be much smaller than initially estimated. One research team used a galaxy distance measurement database and the Tully-Fisher relation to recalculate. Their result was only about 230 million light-years, nearly 10 times smaller than the original estimate. In that case, the void's boosting effect on the Hubble constant would no longer be sufficient to explain the entire discrepancy alone. So, the current situation is this. The void's existence is almost certain, but exactly how large it is, how deep, and how strong its contribution is to the expansion rate all remain up in the air. Scientists must continue to collect more precise data to determine if this mysterious cosmic depression is a key piece of the Hubble Tension puzzle or just a secondary fragment in a much larger enigma. In 2023 to 2024, astronomers used the DESI project to map the nearby universe at the highest resolution to date. The results showed that massive low-density regions like the KBC are not isolated. This local void beneath our feet may simply be a typical node in the massive cosmic web. But don't let this make you think the universe is any less mysterious. Quite the opposite. Precisely because it is not unique, scientists are even more eager to figure out what role it played in cosmic evolution. Besides its potential connection to the Hubble tension, there is an even more thought-provoking hypothesis. If we weren't inside this void, but were instead located in the outside world, what kind of universe would we be observing? Would our observations and even our understanding of the laws of physics be fundamentally different? Regrettably, the boundary of this void is despairingly far from us. With existing technology, humanity may never personally fly out there. But the allure of science lies in imagination. What if one day we possessed nearly infinite time and a space travel technology that completely upended physical limits? What would that journey to the void's edge actually feel like? Strap in, because this voyage is guaranteed to be bumpy. First, you'd need a spacecraft that is utterly unlike any vessel we have now. It would need to withstand immense acceleration and shield its crew from cosmic rays and intense radiation. The most crucial factor is speed. Without sufficient speed, this road is virtually endless. For comparison, if the spacecraft's top speed were similar to Voyager 1's, a few dozen kilometers per second, it would take you over 30 years just to leave the solar system. And reaching the nearest star, Proxima Centauri, would take a full 70,000 years. What's worse, Voyager 1 is already one of the fastest objects ever built by humanity. This prospect is anything but encouraging. So let's assume we possess a starship far superior to anything before, and we have infinite time. Starting from Earth, our goal is Proxima Centauri. To survive, we can't instantly accelerate like in the movies. The human body can tolerate a maximum acceleration of 4 to 6 times Earth's gravity for short periods. Beyond this range, blood supply is cut off, especially to the brain. Once overloaded, unconsciousness is instantaneous. To instantly hit light speed in a few seconds, like in Star Wars, you'd face an impact of 6,000 Gs, literally crushing you into a human pancake. Therefore, we adopt a steady approach. The ship accelerates uniformly at 1 meter per second every minute. The first minute, just 1 meter per second. 10 minutes later, 10 meters per second, accumulating at this rate. Following this rhythm, it takes about 13.5 days to reach the edge of the solar system, where the solar wind ceases. This is also called the heliopause. This achievement leaves Voyager 1 and 2 far behind. They took 35 and 41 years, respectively, to travel the same distance. We reached it in under 2 weeks. As the ship leaves the solar system, its velocity is already approaching 19,000 kilometers per second, roughly 10% of the speed of light. Sounds incredible, but on the cosmic scale, this is just a slow crawl. Out here, communication with Earth starts to get tough. Radio signals traveling at the speed of light now take 34 hours for a round trip. A message you send will take nearly a day and a half to get a response. It's like texting your crush and only seeing the read receipt the next day. Real-time conversation is officially over. The ship continues to accelerate, pushing into the dark expanse of deep space. The sun behind you gradually shrinks into a single, ordinary point of light in the vast, starlit sea. After approximately 65 days, your velocity is nearing half the speed of light, 93,000 kilometers per second. The distance traveled has stretched to 260 billion miles. That sounds enormous, but it's only 4.4% of 1 light year. At this stage, Einstein's prediction, time dilation, begins to manifest. For objects moving at our high velocity relative to observers on Earth, time on board the ship slows down. Your clock runs normally, but the outside world is speeding ahead. As the starship continues to accelerate, we finally enter the realm predicted by Einstein, time dilation. The faster the speed, the slower time passes on the ship. Compared to clocks on Earth, every minute and second you experience is discounted. When your speed approaches half the speed of light, 10 hours on Earth equate to only 8.5 hours passing on board. Your heartbeat, cellular metabolism, and even your perception of time are fundamentally different from Earth's. If we truly want to reach the boundary of the KBC Void, this speed is nowhere near enough. The only choice is to keep accelerating. Before long, the ship's speed breaks through 90% of the speed of light, reaching approximately 168,000 kilometers per second. At this point, time inside the ship is dramatically slower than on Earth. 1 hour on the ground feels like only about 20 minutes to you. Time is starting to work in our favor. By the 129th day, your speed is approaching 99.99% of the speed of light. This is virtually the limit allowed by nature. Scientists have long proven that the speed of light is the universe's ultimate velocity. Only massless particles, such as photons and gravitational waves, can truly travel at the speed of light. Any object with mass attempting to cross that barrier would require infinite energy, which simply does not exist in the universe. For example, the Large Hadron Collider accelerated protons to 0.9999991 times the speed of light. The velocity reached 299,792,455.1 meters per second, just 3 meters per second shy of the limit. But to squeeze out those last 3 meters per second would require more energy than the total sum of all stars in the universe. Nature has established a hard boundary here. The speed of light is not a goal. It is an absolute, impenetrable wall. In 1991, humanity detected a cosmic ray particle, nicknamed the "Oh my God" particle. Its speed was so close to light speed it was almost indistinguishable. The energy it carried was equivalent to a baseball flying at 58 miles per hour. A subatomic particle invisible to the naked eye possessed enough kinetic energy to pierce a cave's door. This is the true picture of energy exploding exponentially as we approach the speed of light. And so, our starship continues its journey at 99.99% the speed of light, becoming one of the most dangerous moving objects in the cosmos. Theoretically, the energy it stores could surpass that of a supernova explosion. If it were truly able to break the speed of light, the ship's mass would approach infinity, and accelerating an infinitely massive object requires infinite energy. Physics would completely break down under these conditions. Reality would collapse under this pressure. Nature uses this limit to tell us that only things without mass can truly travel at the speed of light. At this extreme velocity, time on the ship slows down even further relative to Earth, to roughly 1/70,000th of the time on the ground. You won't feel anything unusual yourself. Your heart and clock are ticking normally, but the world on Earth is racing ahead at 70 times the speed. As you approach Proxima Centauri, 4 light years from Earth, 4 years have passed on the ground, but only about 20 days for you. The rest of the journey is even more mind-boggling. Over 1,400 years pass on the ship, while Earth goes through 100,000 years. The civilization that saw you off may have long perished, and yet you are still sailing. Finally, after traversing approximately 230 million light-years of long darkness, you arrive at the edge of the KBC Void. The ship's clock shows only 3.25 million years have passed, while Earth has gone through unimaginable epochs of change. The space here begins to change dramatically. The number and density of galaxies are about 20% higher than inside the void. The distribution of dark matter is also enhanced. The immense gravity forces the ship's navigation system to execute corrections. You have finally broken into the universe's large-scale structure. Galaxies cluster together like chains, forming colossal superclusters. The entire space is filled with pulls and interactions, no longer that silent wilderness found inside the void. Yet, even in such dense regions, what we see is still just the tip of the iceberg. Astronomers estimate there are at least 100 billion to 200 billion galaxies in the observable universe. However, within the scope of what we can observe, the true number could be as high as 2 trillion or even more. What we call the observable universe is merely a window defined by the speed of light. Based on the travel time of the oldest photons, the radius of this window is between 45 to 47 billion light-years. That is a colossal sphere with a diameter approaching 93 billion light-years. The problem is, the age of the universe is measured at around 13.7 billion years. Given only that time, the universe's diameter shouldn't be nearly this large. This implies two possibilities. Either the universe is older than we think, or its history of expansion is more complex than any model suggests. The universe we see now is essentially a snapshot cut by the speed of light. The light from any object more distant than that simply hasn't had time to reach Earth yet. Therefore, for us, it is a region of complete darkness. But this does not mean the edge of the universe ends right there. On the contrary, it implies that beyond our world, there may be infinite space awaiting discovery. Ever since Edwin Hubble proved that the universe is expanding, people knew that galaxies were not only moving away from each other, but the farther away they were, the faster they receded. He found that for every increase of 1 megaparsec in distance, a galaxy's recession velocity would increase by about 500 kilometers per second. This relationship is known as the Hubble constant, and the observable boundary defined by the speed of light and the expansion rate is called the Hubble volume. Observable here does not refer to telescope resolution, but to the physical limit of the speed of light itself. Looking at the night sky is essentially time travel. Every point of light twinkling in the night sky is what that celestial body looked like long ago. Some stars are millions of light years away from us. The light they emit takes millions of years to reach Earth. More distant galaxies can take billions of years. We are seeing images of the past, and anything beyond our world, even if it exists, can never be delivered to us by present light. So, what exactly is beyond our world? This is a question astronomers still cannot answer. To speculate about the conditions out there, we first need to understand the universe's overall shape. By observing the large-scale geometry of space, scientists have found that the universe is almost perfectly flat, like a sheet of paper. If space is truly perfectly flat, then it is likely infinite. What does an infinite universe imply? It means that if you travel far enough, you will eventually encounter all possible combinations. Not only countless stars and galaxies, but even solar systems identical to your own, the same Earth, and countless other versions of you. In some corner, a parallel version of you might be having breakfast, while yet another version of you decided to skip the meal entirely today. It sounds like science fiction, but an observation in 2008 made this idea even more intriguing. Astronomers discovered that a massive collection of galaxy clusters were all moving collectively in the same direction at over 3 million kilometers per hour. This phenomenon is called dark flow. This large-scale motion is entirely beyond the prediction of the standard cosmic model, suggesting that outside our world there might exist a colossal entity capable of exerting enormous gravity. Perhaps an aggregation of matter and energy beyond our comprehension, or even the influence of another universe. Speaking of giant structures, the largest known monster in our observable universe is called the Hercules Corona Borealis Great Wall. It spans a staggering 10 billion light-years, occupying about 11% of the entire observable universe's extent. To fly from one end to the other would take a full 10 billion years, even at light speed. What's even more incredible, this cosmic Great Wall formed just a few billion years after the Big Bang. This far exceeds the speed allowed by standard theories, as if someone had sketched out the blueprint on the canvas of the cosmos in advance. Some cosmologists further propose that, after the Big Bang, innumerable bubbles may have formed within the expanding space. Each bubble is an independent universe with its own set of physical laws. Even more astonishingly, if space itself is infinite, then these bubbles can also spawn an infinite number of infinities. No matter how far you travel, you will never reach the next bubble, because the space between them is still expanding. You might ask, can humanity ever develop technology advanced enough to see these worlds beyond our world? Sadly, the answer remains no. Even if our civilization existed until the very end of the universe, the speed of light and cosmic expansion will continue to render more and more regions forever unable to establish contact with us. The light emitted by objects beyond 19 billion parsecs is destined never to reach Earth. However, this does not mean we are completely helpless. New generation space telescopes, like the James Webb Space Telescope, already allow us to peer farther back in time, capturing the faint light from the universe's infancy. It acts like a time machine, giving us a glimpse into a more distant past, even if we can never take that step outside our world. So, the question ultimately comes back to you. What do you think is hidden in the darkness we cannot see? If the universe is truly infinite, is it possible that billions of light years away, there is someone exactly like you, performing the exact same action as you are now? Regardless of whether your answer is yes, no, or temporary silence, one thing is certain. That darkness will not stop expanding because of our imagination. Galaxies are still receding. Space is still stretching. Every second pushes more regions toward a place we can never reach. Telescopes can only capture a finite number of photons. The true universe is far vaster than what we see.